Hey guys, welcome. Today we'll be talking about how to train Llama 3.2 on a question answer dataset. So first we are connecting to our Google Drive here. If you go to Google Drive, create a folder that is question answer. Within that we have training backup. Within this folder we'll be saving all the training file that will be generated during training. And then we have Hugging Face token. So it has access token. To create the Hugging Face token, go to Hugging Face, sign in into your account, then select access token here. After selecting access token, click on create new token, and here give write access, give a token name, so let's say 22, and create token. So in this way you have created successfully the token. Now copy the token and put it in a JSON file which is here in your folder. Now after that, when we connect to the Google Drive, after that we are installing all the required libraries. After installing all the required libraries, here we are reading that JSON file and we are loading the Hugging Face token. Then after that we are setting up the seed value for randomization. So we are doing this because by doing this will ensure that experiments can be repeated and results are consistent. After that, here we are using this dataset. If you want to check the dataset, this is the link for the dataset, and you can see it has question, answer, and context. It has other columns also. So after loading the dataset, we are converting that into a Panda file. So here you can see we have questions, answer, and then context. We have ticker and filing. So these two columns are not required. We'll be focusing on these three columns. Now here we are using this Llama 3.2 1 billion instruct model, and this is the Hugging Face space for that model. You can explore the model here. You can work with other model also, but here I'll be working with 1 billion instruct model because I have limited RAM and GPU in Google Colab. After that, here we are loading the model. So basically we are loading the model onto this folder. So this is the folder Hugging Face model, and within that we have this Llama 3.2 1 billion instruct model. So basically we are downloading the model once onto our Google Drive, and we are using the model again and again whenever we want to run this notebook. So this is downloading the model here. Now let's understand what is token and embedding. A token is the smallest unit of text that a large language model processes, such as word, subword, punctuation mark, or special character. Tokens are the output of the tokenization process and are mapped to numerical IDs based on the model's vocabulary. Now embeddings. An embedding is a dense vector representation of a token or sequence of tokens in a high dimensional space. Embeddings capture semantic meaning, so tokens with similar meanings have similar vector. So if you want to know more about tokenization, how tokens are created, you can go to this video. So this is a very good video from Andres Karpathy. So you can go through this video, you'll get a better understanding of how tokens are created. Now let's understand how tokenizer is trained for Llama 2. So to train the Llama's tokenizer, they collected a massive training corpus or trillions of tokens, run sentence piece or BP training. So basically they start with characters or tokens, then iteratively merge the most frequent pair of symbols, for example fin and cial, that becomes financial. Now each merge add a new token to the vocabulary. So this is a general process of training this tokenizer. Now each word is assigned to a unique integer. So Llama 3.2 has a vocab size of 32,000 and the IDs go from 0 to 31,999, and it has some special tokens. So for example, this sentence will be mapped like this. So U will be 312, space R will be 456, financial will be 2201, assistant will be 3309, and dot will be 29889. So let's say if we have a word that is not present in the vocab of the tokenizer, For example, microfinance. So if the word is not in the vocab, sentence piece or BPE breaks it into smaller known pieces. For example, microfinance will be broken into micro and finance, and then it will be mapped into a particular with their respective particular IDs. Now the mapping from tokens and ID is fixed once the tokenizer is trained. So for every time we tokenize financial, we'll get the same ID. So this ID matches the row in an embedding matrix of the model. So basically the model has an embedding matrix. It is of this size, vocab size and hidden dimension. So especially all the rows represent vocabs and all the columns represent this hidden dimension, the dimension of the multi-dimensional vector. And this, when we do this token mapping thing, it maps the rows in the embedding matrix of the model. Now where does this embedding matrix live? So the tokenizer only knows financial 2201. So it just convert this word into this numerical format. Now model has an embedding matrix. So embedding matrix, we have vocab size into hidden dimension. For Llama 3.2 we have 32,000 tokens with 2048 dimension. So basically we have 65 million parameters just for embeddings. So what embeddings are? So each token ID is a row in that matrix. That means you can see each ID is a row in the embedding matrix, and here these are the dimension of the embedding matrix. So when we pass this token information or this, so we converted our text into this token and we were passing this into our model, the model immediately replaces each token to each ID, each token ID with the corresponding row. Now while pre-training Llama from scratch, it tried to learn general language ability by predicting the next token in massive raw text. So this is called causal language modeling. So for this sentence, it first takes the input the, it targets space talk, then for input the and space talk it target space market, then for the space stock space market it targets a crust. So it goes on till the end. So at each step, model predicts a probability distribution over the vocabulary compared with the actual target using cross entropy loss. Now during backpropagation, it updates embeddings, so similar words map to similar vector as well as transformer layers. So it learns grammar, semantic and word facts. So basically during training, the values of embedding matrix are initialized randomly. Then we pass the text and we create the token IDs, you can see, and then we do a embedding lookup in the embedding matrix and we extract the relevant embedding vector. Now the embedding are passed on to the further layer, and then all the transformation work happens, and then it calculates the loss, and using this loss during backpropagation we update both transformer layer as well as embedding matrix. Now during inference, similarly we convert the text into tokens and we do the lookup or embedding lookup in the embedding matrix, and then we pass the embedding vectors to the next layer, and then instead of loss we take logits and softmax and sample the next token. Here training, we do the lookup and we calculate the loss and we update the embedding and layer parameters. During inference we do the same lookup, we don't calculate any loss, we don't do any kind of update, we do predict the next sample token. Now let's see how to use tokenizer. So here we are importing the auto tokenizer from transformer library, and then here we are passing the local model directory. So this is the directory where we have downloaded the model, you can see here. Just a second, here this is the directory. After loading the tokenizer from that directory, we are assigning this paired token to EOS token to paired token, because Llama doesn't have a paired token. It's a general practice to add EOS token as paired token. Then we are adding the token ID also, and then we are saying that we need to pair on the right side. So this is because, let's say we have selected a max token size that is 100. That means we'll be dealing with sentences which has hundreds number of tokens. If a sentence has, let's say, 50 number of tokens, so we'll pair this token on the right side of that text to make it 100. Now these are the special tokens in this tokenizer, you can see here. After that, here we are creating our instruction style format. So currently we have our data in separate columns. Now we're combining all this data and we're creating an instruction style format for Llama 3.2. So for system prompt, for the role of system, we are creating this: you are a helpful financial assistant. Answer strictly from the provided context. If the answer is not present in the context, reply I don't know. So we are using that as a content, as a instruction for system role. For user role, we are taking the context from the context column, and then we are taking the question from the question column. Now for the role of assistant, we have answer column here. Now here we are using the tokenizer to apply this format. So for example, if this is the text we have in our data set, it will be converted into this format. You can see we have added the special tokens here. For the we have specified the role of system here. We have specified the role of you can see this is the system, and then here we have the role of assistant. Here we have the role of user. After that, we are applying that to our data set, and we are creating this text column. You can see all this information are combined and this column is created. Now let's find the maximum token length, or maximum sequence length. So this is the length which will be used for training and as well as inference. So we are plotting, we are going through the entire text column and we are plotting the distribution here, and you can see we have a skewed distribution. That means we have outliers here. So we have for 95th percentile we have 238, for 99th percentile we have 307, we have mean that is 160, and we have max that is 1134. So we'll be taking 99th percentile value, that is 307. You can see, so the max length will be 307. Now after that, we are applying that information here, you can see, and then we are creating the token IDs, and then we are converting the data frame into a dataset object, and we are creating trend and evaluation dataset. So when we do that, we have this many number of data points in training and this many number of data points in validation. So this is one sample. This is our raw text, and that this raw text has been converted into this tokenized form. You can see, so model will see these tokens. Now let's understand how we are training the model. To train the model, we are following a parameter efficient fine-tuning technique using QLoRA. Now QLoRA is an extension of LoRa. Now LoRa stands for low rank adaptation. So in this technique, instead of fine-tuning all model parameters, only fine-tune a few low rank matrices inserted into certain layers. So parameters of the base model are frozen. Extra trainable parameters will be 0.1 to 1% of original model. So you can see we are having a huge saving in memory. So for example, if the base model is of 7 billion parameters, it will take around 28 GB in AP16 format. When we do full fine tuning, we need 28 GB trainable parameter. Now if we use LoRa, so the trainable parameter reduces below 200 million parameter, and memory we need 10 GB. So you can see we have a huge saving in this way. Now QLoRA is quantized LoRa. This extends the LoRa by loading the base model in a 4-bit quantization using bits and bytes. So quantization, storing weights in a fewer bits, reduce memory massively. we still insert LoRa adapters on top. So you can see base model are loaded in quantized format and the weights are frozen. And LoRa adapters are small FP16 format which are trainable. So you can see if the base model is 7B parameters, we have memory size of 28 GB. So if you quantize that into 4 bit, we have a memory footprint of 7 GB. Now for LoRa adapters we need additional 2 GB. So total 9 GB of requirement for this quantized format. So we are getting a huge memory saving if we use QLoRA. Now here we have loaded the model in 4 bit, but the LoRa adapters are in either FP16 or BF16. Now how 4 bit and BF16 are used during training or inferencing? So basically two parts of your Finetune model. So we have two parts of our Finetune model. Base model is frozen, stored in 4 bit compressed form. LoRa adapters trainable, stored in FP16 half precision form. So for during forward pass, the base layer weights are compressed in 4 bit, but we cannot do directly math using 4 bit because this is too crude. So bits and bytes has a special code that reads the 4 bit weights, expand them into temporary higher precision numbers like FP16 or BF16, multiplies with the input and gives the base output. So basically the math is happening in FP16 or BF16, not in 4 bit. Now the LoRa part is already in FP16, so it just multiplies normally. Finally the two results are added together in FP16. So your final output is a normal FP16 tensor, even though the base model were stored in 4 bit. So basically we are converting the 4 bit values into FP16 or BF16 on the fly. Now during back propagation, gradient flow back through the paths. The base path is frozen, so we ignore these gradients. The LoRa path is trainable, so we update these tiny matrices. So that's why we save only LoRa after training. Now why it works? 4 bit base, that is frozen knowledge, captures general language patterns. LoRa adapters, that is like FP16 patches, small corrections added to specialize the model for a question answer task. So during forward pass, they always combine to form the final answer. During backward pass, only LoRa gets tuned, base stays as it is. Now inference after training. So we have two options to do inferencing after the training. We can load the base model in 4 bit and we can load the LoRa adapters in 16 bit. So this is memory efficient, good for GPUs with less RAM. Another way is to merge LoRa adapters into base and create a full FP16 models with updated weights. So this is if you have a higher capacity GPUs, and this is if you have a lower capacity GPUs. Now here we do a 4 bit to FP16 conversion during the forward pass. So does it slow all things down? Yes, it does a little bit. So every time a layer is used, the FP bits must be quantized into FP16 or BF16 before multiplying with input. The step adds some overhead compared to using normal FP16 weights directly. Yes, it does, but we have a huge saving in memory, so people are using this. So when to use QLoRA? If we take LoRa, you can see base model stored fully in FP16 needs lots of GPU memory. Example, Llama 7B in FP16 need 28 GB GPU RAM. So for QLoRA, base model stored in 4 bit, 4x smaller as compared to this thing, and then needs much less GPU memory. So basically we need 6 to 8 GB of GPU RAM. That means we can fine tune on a single consumer GPU. So LoRa is faster, but using QLoRa we have a huge memory saving. Now the slowdown, so conversion of 4 bit into FP16 or BF16, is it really bad? So not usually. it is not that bad. Dequantization is implemented with optimized CUDA kernels, so it's pretty efficient. In practice, QLoRA training is only 10 to 15% slower than LoRa, but the memory saving are 4x, which often makes it the only realistic option. Now, FP16 or BF16. So basically, we talked about how 4-bit parameters are converted into FP16 or BF16. Now, which parameter controls that? So we have something called BNB underscore 4-bit underscore compute underscore D type. So this parameter, if we give B416, so it converts the 4-bit values into B416. So basically we have seen that we have loaded the model in 4-bit, but we have loaded the LoRa parameters in FP16 or BF16. So how does that work? So generally, if we set toss D type, that is BF16, the LoRa weights will be in BF16. If we set toss D type, that is FP16, the LoRa weight will be FP16. Now, when we use this code, PEFT insert extra linear layer for the LoRa adapters. These layers are initialized in the current compute D type of the model. So if we initialize the model in FP16, the LoRa adapters will be FP16. If we initialize the model in BF16, the LoRa adapters will be BF16. They are not passed through the bits bytes config, so quantization never touches them. So here you can see we are loading the base model in 4-bit configuration using bits and bytes config, and then you can see this is auto model for causal LLM, and here we are loading the model. We are using this quantization configuration, and then here we are setting up some parameters, that is gradient checkpoint enable for memory efficiency, and this use case is false. This is best for training. Now this is the model we have loaded in 4-bit configuration. Now for PEFT we are using like this. So here we have LoRa config. So the R is the rank LoRa rank. This is the scaling factor. This is the dropout applied on the LoRa layers. On these layers, LoRa adapters will be applied. So here we have selected toss D type, that is BF16. Hence, all the LoRa adapters will be BF16. So after like combining everything together, we have, you can see we have, this is the trainable parameters and this is the total number of parameters. You can see we have a huge saving here. Now here we are checking whether this column exists or not. Then we are setting up our output directory. You can see within the training backup. So basically this is the folder, and within that we are creating this folder. Within that, all the checkpoints and all the files during training will be saved. And if you want to see the TensorBoard log, you can use this command. Now let's understand the parameters that will be used in training. So we have output directory, then we have per device training batch, that is number of training sample processed per GPU in one forward and backward pass. Then we have per device eval batch size. This is the same as like number of training samples processed for GPU but for evaluation. Now we have gradient accumulation step, so accumulates gradients across multiple mini batches before updating weights. So effective batch size would be 4 into 2, that is 8. So this is useful when we can't fit larger batches into GPU memory. Then we are using page Adam in 8-bit. Now we have training epoch, that is 1. We have this as learning rate, and then we have one more step, that is 20. Then we have max grad normalization, so this is gradient clipping threshold. We have evaluation strategy, that is step. So here after every eval step we do the evaluation, and then here we can set up epoch. So at each end of the epoch we can do the evaluation, but we are using steps for evaluation strategy. So this is eval step, that is 20. So we do run the evaluation after 20 number of steps. Then we have save strategy, that is also step. So when to save checkpoints, then we have save tapes, that is 20. So after 20 number of steps we'll be saving a checkpoint. Save total limit 2, that means we'll be keeping only 2 checkpoints, not more than that. Then we are using logging step, that is 10. Then AP16, that is true. Then we are reporting to tensor board. Then here you can see load base model at the end, that is true. And then metric for base model, that is loss. So we are finding the base model based on loss. And then we are LR schedule type, so we are scheduling the learning rate using cosine learning scheduler. Now for SF trainer, we have model, we have training arguments, all these arguments, and then we have training data set, evaluation data set, data collector, we have data set text field, because we are working on this text field, and then we have max sequence length. So this max sequence length we got earlier from the graph, remember, from the quantile graph, from this graph. Now this is done, this is done. So what is a data collector? So generally when we use tokenization function, this produces input IDs and attention masks, but it doesn't produce any labels. Our model needs both input IDs and labels to compute loss during training. So using data collector, it takes the already tokenized input IDs, pad them if not already padded, creates labels, a copy of input IDs. So the model is trained in a causal LM way. So basically it is creating like this. Now here you can see these are the parameters we have discussed earlier, and then here this is the data collector, and this is the supervised fine tuning trainer. Now when we do train, you will get logs like this. So we are going for only one epoch, and these are the number of steps you can see. Now you can use this code to resume training from any checkpoint. You can see we are passing the checkpoint here and here. After that we are saving the LoRa adapters and training. So training is completed now, and we are saving the LoRa adapters and training into this in this folder. Now you can see this is the same model and this is the folder. So we are saving all these files when we run this code. Now you can see, so here we have this adapter config. This is the metadata or config for LoRa adapters. You can see adapter config. Then we have adapter model dot shape tensors. So these are the actual LoRa weights. Then we have redmin.md. Then we have special token maps JSON. So maps tokenizer special token. Then we have tokenizer configuration, tokenizer hyperparameter, all the configuration. Then we have tokenizer JSON. So the full tokenizer vocabulary and merge rule. So we have all these files here. Now let's do inferencing. So first method is to load the model and LoRa adapter separately. So we are doing that. We are loading the base model first. Then you can see this is we are combining the model with LoRa adapters. You can see here this is the prompt we have prepared, and this is the result. So this is the inference result, you can see. Now let's merge base model and the LoRa adapters together and create a standalone Hugging Face model. So we are loading the base model and adapters separately, and we are merging everything together, and we are saving the model. You can see. So basically this folder will be created, and these are the files for the combined model. So after that, here we are using that standalone model, and we are doing the inferencing. You can see here. Now let's do evaluation on the evaluation dataset. To evaluate the performance of the model, we have some evaluation matrices. So extract exact match, that means if the model answer exactly matches the ground truth. Then we have rules L, that is recall oriented understanding for distinct evaluation. Now here, if overlap between sequence of words focusing on longest common subsequence. Then we have blue score, that is n-gram precision, how many predicted words appear in the reference that matters. Then we have meteor, that is word overlap but with semantic awareness, that is synonymous, stemming, paraphrases. Then we have F1 score, that means harmonic mean of precision, that is how many predicted tokens are correct and recalls how many reference tokens are retrieved. Then we have BERT score, semantic similarity between prediction and reference using BERT embedding, not just word overlap. So these are the score we'll be using to evaluate our model performance. Now this is the code we are running. We are going through the evaluation dataset completely, and we are creating an Excel file combining all this code. So when we run this file or run this code, we'll get logs like this, and an Excel file will be generated. So here this file will be generated, and you can see we have context, we have user query, we have prediction. This is the fine-tuned model, and this is the base model, and this is the actual test, and these are the score you can see. So basically you can see the actual prediction should be like this. Our model is predicting this, so this is good. And here the base model is saying I don't know. And for second thing, you can see our base model has given a longer prediction, but the actual prediction would look like this, and our model is predicting like this. For this thing, this is saying the base model is saying I don't know, model is predicting good. You can see Eli and Lilly and the company manufactures and distributes its products through facilities in the United States, including Puerto Rico and in Europe and Asia. So Eli and Lilly company manufactures and distributes its products through facilities in the United States, including Puerto Rico and in Europe and Asia. So semantically they both are same. You can see we have a lot of I don't know for base model, but we have good prediction if you compare this and this in case of our fine-tuned model. And these are the score if you want to compare. So guys, I hope you understood how to train Llama 3.2 on a question answer system using QLoRA method. So if you have any doubt, please mention that in the comment. If I missed something, mention that also in the comment. I'll try my best to address those. Also, please like, subscribe and share. I'll see you in the next video. Till then, take care.